All right, this section is almost completely word problem oriented. It's meant to be an application section for derivatives. It's referred to as related rates. You're going to find that the level of word problem in calculus can be pretty treacherous. And I think the best idea here is to do a bunch of examples, but explain what I'm doing and the general setup and how I look for things and things of that nature. So we'll get right into it. And the first example says, each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? So, we are given some information here. Let's see what it is. If you have a square, let me just draw a picture of it. Then you generally would label it something like x by x. And we're speaking of the area of a square. The area of a square is simply x squared. Each side of a square is increasing at a rate of 6 centimeters per second. So that is a piece of information that you're given. Increasing at a rate of 6 centimeters per second. Well, how long is each side? Well, each side has length x according to my picture. So I know that this statement here, this first sentence, tells me each side of a square is increasing at a rate of 6 centimeters per second. That dx over dt equals 6 centimeters per second. They just gave me the rate of change of one of the sides. Now what I have to do is try to relate this to area somehow. And how do I do that? Well, you're going to assume that everything is a function of time t, because x is changing as t changes, and a is changing too. As x gets bigger and bigger, you can visualize a larger and larger square being drawn. So the thing that you have at your disposal is to take the derivative with respect to t of both sides. And then take your derivatives as normal. A is a function of t, so I can simply write this as dA over dt. Now this next one, you have x is inside of squares, so you have to use the power rule, 2x to the first power. But now you have to multiply by the derivative of x with respect to t, because that is inside of there. X is a function of t. Let's see what they're asking us for. They want to know what is the rate, at what rate is the area of the square increasing when the area of the square is 16 centimeters squared. So, well, I don't know this, but it's asking me for that. At what rate is the area of the square changing? So this is the rate that the area of the square is changing. I do not know x until they tell me at a equals 16 centimeters squared. When a is 16 centimeters, I know that x has to be 4. 4 by 4 makes 16. So I have 2 times 4. And then you're given this information here times 6. I'll put in my units when I'm done. So 2 times 4 is 8, times 6 is 48. So I have dA over dt equals 48. Now this is the time to put in your units. Centimeters squared per second. All right, a snowball melts, so the surface area decreases at a rate of 1 centimeters squared per second. Find the rate at which the diameter is changing when the diameter is 10 centimeters. The surface area is decreasing at a rate of 1 centimeter squared per second. Find the rate at which the diameter is changing when the diameter is 10 centimeters. Now, writers of calculus textbooks and calculus teachers believe that you should have most of your geometry formulas memorized to the point where you can just recall them right off the top of your head. Apparently, that is not the case, as students don't do that. Luckily, nowadays, if I wanted the formula for the surface area of a sphere, and you have to assume that the ball stays sphere-like through its whole melting phase, if I couldn't remember the formula, I would say, "Okay, Google, give me the formula for the area of for the surface area of a sphere," and it would send me results. I'd click on it. It's that easy nowadays to find them, so it's not like they're hard to get to them. So let's go ahead and do that. Let me put down the formula for the surface area of a sphere. It's 4 pi times r squared. That's the surface area of a sphere. And I don't need to tell you what r is. You know that that's the radius. So this is the thing that will be doing the changing. I somehow need to connect that or relate its changing to the changing of the diameter. Well, I do know this, that the radius is 1/2 of the diameter. So I get 4 pi d over 2 squared. Now I see I have a connection. Pi is just a number. D is connected to A. That's exactly what I want. I can simplify this a little bit before I take the derivative. This will be d squared over 4. The 4's will cancel, so you get pi d squared. Now I have a connection between A and D. Let's go ahead and take the derivative with respect to t. dA over dt equals 2 pi d times dd. I know that's a horrible notation, but it's only going to be there for a short period of time. Now I'm ready to plug in my stuff. The surface area decreases at a rate of 1 centimeters squared per second. I'll put in the units later, but I do know that it is decreasing at 1 centimeters squared per second. So I'm going to put a -1 there to indicate that it's getting smaller. Find the rate at which the diameter is changing when the diameter is 10 centimeters. So I'm going to plug that in for D. So I'll have 2 times pi times 10 times dd over dt. And that's going to be 20 pi. If I solve, I'll get dd over dt equals -1 over 20 pi. And since we're talking about the diameter, it's measured in centimeters per second. Notice the negative indicates that the diameter is getting smaller. All right, we have two cars moving from the same intersection. One car travels south at 60 miles per hour and the other car travels west at 25 miles per hour. Let me draw a picture of this. Okay. So this guy here is going 60 miles per hour in that direction. And this guy up here is going 25 miles per hour to the left. And at what rate is the distance between the two cars changing 2 hours later? Well, the distance between these two cars is the length of this hypotenuse. So I'll call that capital D just to avoid the two little d's again. So, and while I'm also at it, let's call this X and Y. And you should know there's a pretty simple connection between these using the Pythagorean Theorem. You know that d squared equals x squared plus y squared. I need to connect at what rate is the distance between the two cars changing. So that's this guy right here. There's our distance 2 hours later. Now, I got to connect it to time then. And the easiest way to connect it to time is by taking derivatives. So let me go ahead and do that. If I take everything, the derivative of everything with respect to t, you first use the power rule on everything. You'll get 2d, but then you'll get dd over dt according to the chain rule. The same goes for all the other ones because they're both X and Y are both functions of t also. Y gets bigger as t goes on, and x gets bigger as t goes on. So I'm going to get 2x dx over dt plus 2y dy over dt. Now, one thing I can do really quickly is get rid of all of these 2's. I'll just cancel them all out. And I'll put in the stuff that I know. I know the south car, which is y, travels at 60 miles per hour. So I have d dd over dt equals x times, and x is traveling at 25 miles per hour. So I'll put a 25 there, and y was traveling at 60. Now all I need to figure out is what dx and y was 2 hours later. So when that is 2 hours, here's the kind of a picture we have. Y is going 60 miles an hour for 2 hours. It would go 120. X would have gone 50 miles. And then D, I would have to use the Pythagorean Theorem to get that. D will equal the square root of 50 squared plus 120 squared. And let me see, that's 2,500 plus 14400. That equals 16900. And this is not so bad. This equals 130. So I have 130 dd over dt equals, now the x was 50. And the y was 120. And that equals 1250 plus 7200. And that is 8450. So I have 130 dd over dt. Now I'll divide by 130. dd over dt equals 8450 divided by 130. And d, this distance here, would have been measured in miles. So that would be miles per hour. If you feel like simplifying, go ahead. A trough is 10 feet long, and its ends have the shape of an isosceles triangle that are 3 feet across at the top and have a height of 1 foot. If the trough is being filled with water at a rate of 12 cubic feet per minute, how fast is the height of the water changing when the water is 6 inches deep? So, a picture would look something like this. I'll try to do a three-dimensional look to it. That side didn't come out so well. So, and then this here would be the middle. Let's see if I can draw. And of course in the back it has a V shape too. Something along those lines. It's a terrible look, but I might be able to do better if we look at it from this angle here. Here's what you have from the bottom. You have water filling up something like this. This is how it will look from the end. And if you turn it a little bit to the side, I hope I can capture it a little bit. You can use the same thing and then do this. I think that may be an easier way to visualize this thing. Alright, so something like that, and then you've got water filling into it. And this is probably the most important piece here. The thing is 10 feet long, so the length of it never changes. but the depth of the water will change as you're filling it up. So let me draw a picture here. We have, this is the original thing. I'll put that there even though that's not the water level. I know that that's 3 feet apart, and I know that the height is 1 foot. And then you'll have the water level in here somewhere, filling up as you go. Now, a trough is 10 feet long, and its ends have the shape of an isosceles triangle that are 3 feet across at the top and have a height of 1 foot. Got that down. If the trough is being filled with water at a rate of 12 cubic feet per minute. So what they just gave you there is that the derivative of volume with respect to time is 12 cubic feet per minute. How fast is the height of the water changing when the water is 6 inches deep? So in order to do this, I probably need to get the volume of the water, first of all. What is the volume of this water? Well, I don't know what it is, but let's call this amount, the height of the water, we'll call H. Okay? And so the volume, V, equals the area of the base times the height. Any kind of what they call prism, an object that stays the same throughout the whole piece, you take the area of the base times its length. So what is the area? Now this is the volume of the water. What is the area of the base? Well, I would have to know the height and the base here. But fortunately, if you look here, let me pull this out. If this were more of a straight line, it'd probably be easier to see. Let's make this flat. This little triangle in here of water versus the entire triangle are similar, because this angle at the tip is the same for both triangles, and assuming that this thing is standing straight up, the water level is level. Therefore, this corner angle up here equals this corner angle in here. This corner angle here equals that corner angle there. So similar triangles. So let me see if I can write this out. We have the one that's a 3 by 1 is similar to the little one, which went like this, which had an H. And let's call this B, because the area of the base is B. So my volume, the area of the base is 1/2 base times height times, let me change this here. I don't want to use height twice. Area of the base times the length. That way I can use height for this stuff here. So the length of this thing is 10 feet. So I have 5BH. V. Now, the problem with this is, while I've related the sides to the volume, I have too many variables here. I need to get this down to one variable. So I somehow need to relate B and H. So can I do that? And you can. If you look, the original triangle is a 3-to-1 ratio. The base to the height is 3-to-1. Therefore, this base to the height is 3-to-1. That's what it means for similar triangles. You take any side divided by that height is equal to this side divided by that height. What you end up then is that 3H equals B. Now I can get rid of B by replacing it with 3H. So this equals 5 times 3H times H equals V. V equals 15H squared. Now, let's take a look at the original problem again and see if I'm getting somewhere. How fast is the height of the water changing when the water is 6 inches deep? The height of the water, perfect. And since I'm going to take a derivative with respect to V, because you were given this piece of information. dV over dt was 12 cubic feet per minute. So dV over dt equals, now take the derivative of the other side, I'll get 30h times dH over dt. Notice that dH over dt is what you're looking to solve. It asks us how fast is the height of the water changing. So, when the height is 6 inches. By the way, everything's been given in terms of feet. This was 12 cubic feet per minute. This h was given in terms of 6 inches. Do not mix inches and feet. Put it in feet. 36 inches is 1/2 of a foot. And you can see the only thing that I have left as a variable is dH over dt, which is exactly what the problem is asking me. So I have 12 equals 15 dH over dt. And then I can finally solve dH over dt equals 12 over 15, or 4 over 5. And what were my units? It was feet per minute. They were doing things per minute. Feet per minute. If you want to put any of these in decimals, I don't care. That seems like the most... All right, our next example. Gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. And its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile changing when the pile is 10 feet high? So what they've given you here, this piece of information, 30 feet cubed per minute, is actually the change in the volume of the thing. They gave you dV over dt is 30 cubic feet per minute. And we have the shape of a cone whose base diameter and height are always equal. So I'll have something like this. Here's my cone. So this height, or that diameter and this height are the same. So it says how fast is the height of the pile changing. So I think I'll call this h, and then I'll call down here h. That'll stand from... But that's really not what I'm going to do. I'm going to have an h versus h over 2 thing. Well, actually, maybe not. Let me see. I need to get the volume. So what is the formula for the volume of a cone? The volume of a cone V equals 1/3 the area of the base times the height. The reason why I say that, the 1/3, if before it's the area of the base times height, if the thing stayed the same all the way through. If it ends in a point, then you automatically get a 1/3 on here. That's the formula. Once again, there's an expectation that you remember some of this stuff. So, the bottom is a circle of radius h over 2. So 1/3. The area of the base is the area of a circle of radius h over 2. Pi h over 2 squared. That's pi r squared right there. And height is times h. Well, this is nice. I now only have one variable connected to v. V equals, let me simplify a little bit. H squared over 2 is h squared over 4, so I have 1 over 12 pi h cubed. Now I can take the derivative. dV over dt equals, once again, bring down the 3, and that'll make it 3 over 12 is 1/4 pi h squared. Now don't forget the chain rule, dH over dt. And that's actually what we're looking for. dH over dt is what it's asking me for. There we are. dV over dt is 30 cubic feet per minute. I'll just do 30. I'll put in the units when I'm done. 1/4 pi. And where was the original problem? There it is. Come back. How fast is the height of the pile changing when the pile is 10 feet high? So my h is equal to 10 times dh over dt. All right, so I get, here I'm going to get 100 divided by 4 will be 25. 25 pi dh over dt equals 30. I'll divide both sides by 25 pi. I get 30 divided by 25 pi equals dh over dt, or simplified, dh over dt equals 6 over 5 pi, and the height is measured in feet, and the time is measured in minutes. So this is feet per minute. Two sides of a triangle are 4 meters and 5 meters in length, and the angle between them is increasing at a rate of 0.06 radians per second. Keep in mind, you should always have your calculator in radians. It will be a very extraordinary circumstance in which we ever do anything with degrees. Find the rate at which the area of the triangle is changing when the angle between the sides of fixed length is pi over 3. I think it may be beneficial to show you what I initially tried to do before I came up with a better idea. And what I tried to do was this. Let's say that's 5, and let's say this is 4. And then you would have, this would be B, H. I need B and H because it says find the rate at which the area of the triangle is changing. So I'm going to need to get dA over dt at some point. And I'm finding it hard to do anything with this. It says, and they're talking about the angle changing anyways. So you could have like a theta up in here, getting bigger. Of course, the triangle is getting wider and wider, but shorter and shorter. So the area is going to be changing. It's just, there are connections, like I can make a connection between B and theta, but I didn't find anything that was really helpful there. I want to find a connection between these things and theta, if I can. So let's write this down for a minute. The area of a triangle is 1/2 BH. Now what made this problem work out really well was when I changed my picture. I instead rewrote it like the following. So I put a 5 there as my base, theta here, this one's 4. Then the height is the length of this, so I can call that h. Well, you can see that h, let me fix that side up. There's 4. And there is h. Now, what I'm going to do, and this is b, remember that. But I don't need that anymore because I have 5. So I can actually take this out. My base is now 5. My height, I don't know yet, but I can get a connection. If you look, let me make this triangle a lot bigger. This right triangle one that's down here. I have h, I have 4, and then I have pi minus theta down here. Since this is on a straight line, it adds up to 180 degrees. So if theta takes up that amount, 180 degrees minus theta takes up the rest. So now I have a connection between the h4 and the area. If you look then, a equals 1/2. I'll keep that there. I'm going to leave the h there, but I want to find the base was 5, and then h, I can connect all of these using sine. The sine of this angle equals opposite over hypotenuse. So I can do sine of pi minus theta equals opposite over hypotenuse. So in fact, where I have an h here, I can change that to 4 sine of pi minus theta. Now this is nice. Now I've connected theta to a, and that's exactly the relationship that I need. Let me simplify a little bit. A equals, we have 10 times sine pi minus theta. Let me take the derivative of both sides with respect to t. D over dt of a equals 10 sine pi minus theta. So I'll get dA over dt equals 10 times cosine pi minus theta. But I got to take the derivative of the stuff inside. So I need to take the derivative with respect to t of pi minus theta. 10 cosine pi minus theta times the derivative of this will be -1, but then the derivative of theta is d theta over dt. So let me simplify. I have -10 cosine pi minus theta d theta over dt. Of course, this is dA over dt. Now let's see what information we do have. Find the rate at which the area of the triangle is changing. So they want me to find this thing, this dA over dt. So I don't know that off the bat. But I do know, find the rate at which the area of the triangle, the angle is increasing at the rate of 0.06 rads per second. So let me put those in there. I have -10 cosine of pi minus, and I think they wanted us to do it for theta equals pi over 3 when the angle is pi over 3. And that was 0.06 rads per second. I'll put the thing in there, the units at the end here. dA over dt is precisely what I was looking to solve. This equals -10 cosine of 2 pi over 3 times 0.06. -10 cosine of 2 pi over 3 is -1/2. So that's 5 times 0.06. And so I have dA over dt equals 0.3. And what were our units? That's all I need to get now. Since the area is going to be something squared per second. So the area is meters squared per second. Meters squared per second. All right, this is the last of my examples. A camera is located 4,000 feet from a rocket that is about to take off. If the rocket shoots straight upward, how fast should the angle of elevation of the camera be changing when the rocket is 3,000 feet in the air, traveling at 600 feet per second? So let's say we have something like this. So the rocket is going 600 feet per second upward. We'll have to put a 3,000 in here when I get to that. We are 4,000 feet away from where the rocket takes off. This is where the rocket, that's the rocket going like this. Of course, it's a right angle. And then the angle of elevation is this. So what the camera has to do is it has to keep moving upward and upward to keep the rocket in view while it's climbing. All right, is there a connection here between, in fact, let's call this H. Is there a connection between these things? the height, and theta. Well, yeah, there's a very simple connection. Tangent equals opposite over adjacent. So tangent theta and then I need to go, how fast should the angle of elevation of the camera be changing? So I need d theta over dt. That means I'll take the derivative with respect to t of both sides. The derivative of tangent is secant squared. So I get secant squared of theta times d theta over dt. That's precisely the thing we're looking for. And then I simply want 1 over 4,000 times dh over dt. And I know dh over dt, so let's see what we have. They want to know what is the d theta over dt at the point when it's 3,000 feet in the air. I do know dh over dt is 600. So let's see what I can get here. 1 over 4,000. And dh over dt was 600. D theta over dt, that's what I'm trying to determine. Now, when h is 3,000, what kind of a picture do we have? When h is 3,000, let me put it down in here. So we have 3,000, 4,000. I had a teacher years ago that told me anytime you see this, you sort of rejoice because this side is automatically 5. You ever heard the 3, 4, 5 triangle? Well, this is it, except it's in the thousands. So this will be 5,000. And there's theta. Secant of theta is hypotenuse over adjacent. So this will be 5,000 over 4,000 squared. Of course, you'd really like to do some simplifying here. I'm going to take out the zeros here. I'm going to get 25 over 16 d theta over dt equals, let me see what I can do on this side. I can take out a 0, divide by 10, and then I can take out another 4 and make this a 15, and then make this 100. Of course, you feel free to use a calculator for any of this stuff. All right, so to get d theta over dt, I'll multiply by 16 and divide by 25. So d theta over dt equals 15 over 100 times 16 over 25. And there's a substantial amount of simplifying that can happen here. I can make that into a 4, this into a 25. I can make this into a 3, and that into a 5. That's what I have. Over 125, and theta is measured in radians, so radians per how fast? Second, because it was going 600 feet per second.